In this unit, we're going to be considering MOSFET amplifiers. And so it's worth noting that we're going to be looking at analog circuits, which are going to be made to amplify analog signals. However, as I've kind of touched on before, our MOSFETs are typically going to be used more heavily for digital logic. So MOSFETs are heavily used in digital logic. And so if you want to see some more details about that, you can look in some of the later chapters in the textbook. Unfortunately, we're not going to have time to get to that in this class or later classes, but you can see how MOSFETs can be used to make things like simple logic circuits or simple memory circuits. But in this unit, we're just going to focus on our analog capabilities of our MOSFETs as amplifiers. Now, just like with our BJTs, we want to be looking at linear amplifiers. In other words, we don't want to be clipping any of our signal. So linear amplifiers, and the main reason we want to do that is so that we can use our superposition principle. So we want to be able to use our superposition, which ultimately just means we can do our DC and AC analysis separately. So we can do DC and AC analysis separately, and then we just bring the two parts together and we can sum them and we can say this is our total response. And so sort of similar to our BJTs, we're going to have that same type of notation. So we're going to have DC is going to be an uppercase parameter and an uppercase subscript. So if we're talking about drain current, we would have ID. So this would be our DC value. We would also have some AC signal, which would be lowercase parameter, lowercase subscript. And then we're saying we also have some total instantaneous drain current, which is just going to be the sum of the two. So we would have lowercase I, uppercase D, which is going to be equal to the sum of our DC and our AC component. So this would be our total instantaneous drain current in this case. So instantaneous. So again, same type of notation that we saw when we were looking at our BJTs, and actually same notation that we talked about way back at the very beginning of the course. And then of course we also have the uppercase parameter, lowercase subscript, which we said is our phasor notation. And sometimes we'll use that interchangeably with our AC terminology, especially when we're looking at our small signal circuit. Okay, so we have these amplifiers, we want them to be linear, and so what does that mean about the actual operation mode of our device? So if we have these linear amplifiers, that means our device needs to be operating in the saturation region. So we want the saturation region. And so this is similar to with our BJTs. Remember, we always said we wanted it to be in the forward active region. And so if we consider just sort of briefly what our curves look like for our MOSFET, so we have something that looks like this, and we had some VDS line, which was separating our saturation region over here, and our non-saturation or triode or ohmic region over here on the left. So of course this was our drain current, and this is our VDS. And so what we can see is if we want to have that linear operation, we want to be over here in the saturation region. And so we'll talk about that a little more clearly, particularly in terms of once we see how we superimpose the load line for a particular circuit. And so over the next few videos, what we're going to do is we're going to develop a small signal sort of analysis approach. So the same way we talked about with our BJT circuits, we're going to look at how small does the signal need to be to consider these amplifiers to truly be linear. We're then going to talk about the specific small signal models for our MOSFETs before looking at specific amplifier configurations a little bit later on.